This takes us now to a very interesting closing section of the course. I wanted to talk about lots of different areas of number theory to build up to Fermat's little theorem. It's called Fermat's little theorem, possibly because there's another theorem of Fermat called Fermat's last theorem. That was very famous because it took hundreds of years to prove. We won't take hundreds of years in this lecture, so we'll concentrate on this one. Maybe in a future lesson on number theory, we can talk more about those other things. Fermat's little theorem lets you solve questions like this. A number to a very big number, modulo something very close. We got some ideas about this when we looked at the powers of numbers and looked at their last digit. We found an interesting pattern that if I looked at what was the last digit, modulo 5, there was something special about 4. We discovered with 5 that if I took any number which was not 0, that if I took that number and raised it to the 4th power, it was congruent to 1 mod 5. This was for any x which was not 0. I like finding facts through patterns, and so that one we found by just doing a standard or routine type of number theory puzzle of taking powers of numbers. We also discovered that x squared was congruent to x mod 2. We also discovered that x to the 5th was congruent to x mod 5. And these last two were true for every x. Now, I want to pull everything together. We have been talking about primes like 11. In a previous lesson, we were looking at what happens when I multiply by 4 modulo 11. 11 was a prime. And here I have 2 and I have 5. Those are also all primes. It turns out that if I look at what happens when I take these powers, certain powers can make me come back to 1 or come back to myself. For that, I want to illustrate that by starting with a nice prime called 11, where we already have a nice diagram. For a prime, 11, let's look again at what was our picture when we were looking at multiplying by 4. If the arrows are multiplying by 4, I have some very, very nice patterns again. 0 multiplies by 4 to itself. And then the rest of this pattern goes 1 times 4 is 4. And the rest of this pattern goes 1 times 4 is 4. 4 times 4 is 16. Reduce mod 11 gives 5. 5 times 4 is 20. Reduce gives 9. 9 times 4 is 36. Reduce gives 3. And this was the first cycle. And we had shown that there is an equal length cycle. And we even know beautiful properties, like it's just multiplying by 2. So this is 1 times 2 is 2. 4 times 2 is 8. 5 times 2 is 10. 9 times 2 is 18. Mod 11 is 7. And 3 times 2 is 6. This is the times 4 picture. When you look at the times 4 picture, then you also immediately see that if I take 4 and raise it to the 5th power, something interesting happens. You see, when I take 4 and raise to the 5th power, all these cycles are the same length. 4 will be in the cycle that has 1, of course, because I take 1 times 4 gives me the 4. Since the cycle has 5 in it, that means that 4 to the 5th will be 1 times 4 is 4, times 4 is here to 5, times 4 gives you 9, times 4 is 3, and the last times 4 takes you back to 1. So we have 4 to the 5th is congruent to 1 mod 11. The important thing, what this number is, this 5 is the perimeter of this cycle, the length of this cycle. 5 is the cycle length. So now I know that 4 to the 5 is 1 mod 11. Well, if I look at my example, I had x to the 4 is 1 mod 5. I also don't always know that the cycle has length 5. Reminding of another thing that we had talked about before, let's look at the mod 11 of times 2. For the prime 11, now if my arrows are blue and they're going by times 2, again, 0 stays by itself, multiplying by 2. But then there was a very long cycle. Everything went into one cycle. It went 1, 1 times 2 was 2, 2 times 2 was 4, 4 times 2 was 8, 8 times 2 was 16, reducing with 11 gave you 5, 5 times 2 was 10, 10 times 2 was 20, 20 reducing mod 11 gave you 9, 9 times 2 was 18, which reduced mod 11 gave you 7, 7 times 2 was 14, 14 reduced mod 11 to 3, 3 times 2 went to 6, 6 times 2 went to 12, and 12 was the 1. So I can draw for you this cycle. 4, 5, 6, I'm counting arrows, 7, 8, 9, 10 arrows. This is a cycle of length 10. 10 length. What that means is that if I take, this is times 2, if I take 2 raised to the power 10, that's congruent to mod 11. That will be congruent to starting here from the 1 and walking 10 steps, because each step is times 2. So it's congruent to 1. I'll go back to where I started. So now I've found that 2 to the 10 is 1 mod 11. I also have that 4 to the 5 is 1 mod 11. I would like to have a theorem that says the same thing no matter what I start with. Because if you look at the other theorem, it was x to the 4 is 1 mod 5 for any x, which is not 0 mod 5. But what can help us to do this is, you see, this is a cycle of length 5. But now I'm going to use that the cycles are all the same length. The cycles are all the same length, and there are 11 numbers in total. Let's not look at the 0. 0 is special. Over here, on the right-hand side, I actually have 10 numbers, 10 non-zero residues. And they will always be split into cycles of the same length. What that means is that the cycle length divides 10. This is always true, whether I have cycles which are times 4 cycles or cycles which are times 2 cycles. Both of these have lengths which are divisors of 10. What does that mean? If I can take 4 to the cycle length, and that's 1 mod 11, then I can take this whole equation and multiply it by itself a few more times. Remember, I'm allowed to multiply equations about congruences. 4 to the 5 is congruent to itself, congruent to 1 mod 11. Now I have 2 copies of this. If I multiply them by each other, then I have that 4 to the power 10 is congruent to 1 mod 11. And this works no matter what the cycle length is. I can always multiply it by itself enough times. Because it divides 10, I will always be able to get to the number to the 10 is 1 mod 11. I can do this as long as my arrow is relatively prime to 11. So what I need here is that this arrow 4 has to be relatively prime to 11. 11 is a prime number in the first place. So what this actually means is that for any x which is not 0 mod 11, what this means is that for any x which is not 0 mod 11, I will have that x to the power 10 is congruent to 1 mod 11. Now I want to go and make this the most general that I can with this argument. I used that 11 was prime. And if I look at how the argument works, whatever the prime is, there's one taken apart, which is the 0. And the rest, all the rest of the non-zero residues, there are p minus 1 of them. There are always p minus 1 non-zero residues. And so the cycle length, since all the cycles will always be the same length, that's going to divide p minus 1. P is my prime number here. So 4 to the power any of the cycle lengths, I can multiply by itself until I have 4 to the power p minus 1. I can always do this, even if I have different kinds of cycles, because the total length of this picture will be still p minus 1 because there is this 1 for the 0 reserved off to the side. So again over here, I get 2 to the p minus 1 is 1 modulo p. Putting the whole thing together, Fermat's little theorem now tells us that if I take any p, if I take x, which is not congruent to 0, mod p, then I have that x to the power p minus 1 is congruent to 1 mod p. And this is what we call Fermat's little theorem. You may notice that we also had seen other types of theorems here. We saw something else, which was x to the power something is x mod p. And that held all the time. Let me go back to this just to make a comment about it. We had that x to the power something is always x mod the thing. I didn't even need the not 0. The only comment to make here is that, well, if I have Fermat's little theorem, this is easy, because I just multiply both sides by x. And, well, there's one case to worry. What if x is 0? Well, it's very easy to prove 0 to the 5th is 0 mod p. So this last case just takes care of the 0 for you. In conclusion, what we have here now is an interesting result in number theory, which, in order to fully understand and prove, it's helpful to know how the multiplication makes cycles. It's also helpful to understand how, in number theory with modular arithmetic, you can multiply by inverses, and all of this structure that we have covered. We'll do one more discussion after this, which will consider how you could use Fermat's little theorem for something interesting as well.